5 years after Planck published his light is created in quantized chunks of energy theory, Albert Einstein demonstrated that light was consumed in quantized chunks of energy as well. This was done using the photoelectric effect. The photoelectric effect is the ability of high-frequency light to dislodge electrons from a metal surface. In this experiment, a vacuum tube contains two plates connected to an external circuit that produces a voltage between the plates. A light source shines on one of the plates. If an electron is dislodged from the metal plate with enough energy to overcome the voltage, it will reach the other plate. This is measured as an electric current. As the voltage is increased, the number of electrons that can make it across goes down. At some point, the voltage is large enough to prevent any electrons from making it across, and the current stops. We can measure and graph this effect for varying light frequencies. Here's what we see. Being a straight line, we can measure the slope. We get energy is equal to a constant times the frequency, and the constant came out to be exactly the same as what Planck had come up with when he studied black-body radiation. So, light starts out quantized, as demonstrated by black-body radiation, and is absorbed quantized, as demonstrated by the photoelectric effect. So it stood to reason that it travels quantized as well. In other words, it's a particle, not a wave. But what about the earlier proof that light was a wave? For that, we revisit the Young double-slit experiment. We've seen Young's diffraction pattern that told us light was a wave. So now let's fire photon particles one at a time at the slits. What happens is that for each photon, the detector registers a hit on the back screen at a single point. And at first, with a small sample, the hits seem random. But over time, we see that the interference pattern re-emerges. Here's a video of the detector plate. It's as if each photon was contributing to the interference pattern, even though there wasn't another photon to interfere with. So, the conclusion is that photons interfere with themselves. Turns out that they only interfere with themselves. They never interfere with another photon. Now look what happens if we detect which slit the photon went through. Here, a detector registers yes if the photon went through the upper slit, and no if it didn't. The detector sees a photon coming through the top slit around half the time. We assume that if a photon went through one of the slits and it was not the top slit, then it must have gone through the bottom slit. Here's the resulting pattern. But this is the pattern for particles. If we turn off the detector, we get the pattern for waves again. This duality puzzled scientists for years and is argued about to this day. A good way to look at it is light propagating through space as a wave. But at any time it interacts with something, it interacts as a particle. In other words, it is created as a particle and absorbed as a particle, but travels through space as a wave. In 1924, Louis de Broglie predicted that this wave-particle duality will work the same for particles like electrons and atoms. By 1927, this had been demonstrated for electrons and atoms. With today's equipment, we can even see it for large 20-atom carbon molecules. So we have light waves acting as particles and particles acting like waves. We call it particle-wave duality, and it is a fundamental aspect of quantum mechanics, and these were the experiments that started it all. So once we understood that electrons travel as waves, they will have a wavelength. Here's the simple derivation conducted by de Broglie. The momentum for light is Planck's constant divided by the wavelength. So the wavelength is equal to Planck's constant divided by the momentum. And we know that for particles, momentum is equal to its mass times its velocity. So a simple substitution gives us the wavelength for the particle as Planck's constant divided by the mass times the velocity of the particle. And if that wavelength is a lot smaller than a photon's, it will enable us to break through the diffusion limit and see things much smaller than a microscope can. So let's take a closer look at this subatomic particle and find out what its wavelength is.